Hello everybody. So we are in this lecture going to look at island arcs. Now island arcs are shown here in these red lines with the teeth on them. And if you haven't seen these before, those teeth are in the so-called upper plate. And then on the other side of the line over here would be the downgoing plate. So if we're looking at the Japan Trench here, the upper plate is the Eurasian plate, and then the downgoing plate is the Pacific plate. And if we look at these in cross-sectional, looks something like this. So here, this would be the Eurasian plate, for example, and then the downgoing slab would be the Pacific plate. Now, this material here that's going down, the basaltic crust and the lithospheric mantle that's sitting on top, that is related to the ophiolite sequence we saw before. So the basaltic crust are the layers 2A and 2B and 3A and 3B, etc. Layer 1, by the way, are the sediments that are sitting on top. Pelagic means deep sea, so when you see reference to pelagic sediments, those are fine-grained muds that are settling out in the middle of the ocean basin. Beneath that, in the basaltic crust, are the pillow basalts and the sheeted dikes and the gabbros. And all of that, the basalts, the dikes, and the gabbros, they all make up that blue basaltic crust that's moving down the trench. And then below that, so this is the moho here, below that is the mantle. And we have the lithospheric mantle, the part that's solid, and below that is the asthenosphere, the soft part. So that solid bit of lithosphere, which includes the basaltic crust, this whole piece here, is diving down. Now, an important aspect of this diagram are these isotherms. So notice that as we go deeper and deeper, we hit the 600-degree isotherm, a little bit deeper still, we have the 1,000-degree isotherm. And we have some isotherms over here. Here's a 600-degree isotherm, and here's a 1,000-degree isotherm. And it gets hotter still as we go deeper. But subduction messes all these up. It creates a little bit of havoc. And in this next diagram, which is just so nicely done in your author's book, you can see the isotherms maybe a little more clearly. So what's happening is we're taking cold material here near the surface and we're shoving it into the mantle at a faster rate than temperatures can equilibrate. So those cold temperatures get preserved here at a much greater depth than they normally would be. So for example, over here in the continent, let's go back to this diagram. If we're over here, we'd have to go to about this depth. Here's the kilometer scale. So that's about 50 kilometers would be about there. This is maybe about 30, 40 kilometers depth. We'd hit the 600-degree isotherm. But notice the 600-degree isotherm becomes very shallow, and then it becomes very, very deep. So here, the 600-degree isotherm, down here in the middle of the subducted slab, is about 150 kilometers depth. And so the way we get that cold material at such great depth is by shoving this material down very, very quickly. And so that's what's being shown here. All of these isotherms are being subducted just like the material is being subducted. What we're really subducting is thermal energy, or in this case, a lack of thermal energy. We're taking cold material and shoving it into the mantle. So now these isotherms here, the 600, the 1,000, and the 1,400, they all occur much deeper than what they normally would be. So I'm going to have an assignment where you're going to interpret those these isotherms, and then you're going to redraw this diagram where in place of basaltic crust and lithospheric mantle, what I want you to do is draw a cross-section so that it looks like an ophiolite sequence. And you'll show that ophiolite sequence going down. In a later lecture, we'll take a look at eclogite and some of the metamorphic reactions that drive plate tectonics. Before we're off the topic of island arcs, I want you to take a look at this diagram, figure 16.2. This shows what's called the Benioff-Wadati zone. I want you to read about that, or Wadati-Benioff zone. I said it backwards. There's a Japanese fellow who first recorded seismic activity at the top of the oceanic crust And then another fellow, forget where he was from, but he made the same discovery at about the same time. And so they call this discovery the Wadati-Benioff zone. It's a zone of earthquakes. And this zone of earthquakes dips very deeply into the earth, and that is how subduction zones were first identified. A little bit later, we're going to make some diagrams using Excel to look at the chemical composition of the volcanic rocks. So there's a little bit of a preview. We'll make diagrams that look like this, and then we'll look at some of these classification diagrams in Excel. Then I'll show you how to make some triangular diagrams as well. These diagrams are a way to figure out what kind of tectonic environment a rock formed in by looking at their chemistry. So if you sample rocks that are very old, let's say Jurassic in age from the Sierra Nevada foothills, did they form as part of the basaltic crust in the middle of the ocean basin? Or are they ancient continental crust that formed at a volcanic front? We can use diagrams like this to figure out that kind of tectonic environment. So we'll see that a little bit later.